So I've developed it further, and it's my life's work really. So, but it's completely incomprehensible, of course, to anyone else. It depends on a new mathematical theory which we finally got published last month. And if mathematics is the theories of values, or this is a different theory which treats pluralities of values, and wasn't our own idea, but we've worked out all the details which the inventor hadn't done so. But what I want to talk about today is a little tiny corner of it where the people in this room probably have more knowledge than I do. So the idea of prospective values is that if you have a program and you can say what the value of things will be after you've run the program, that is a way of describing what the language does. And you can also use that as an execution structure. You've got a structure that says run S and then tell me what the value of E would be, leaves a value on the stack. So how legible is that?
That's good, that's fine.
So x1 plus 2x diamond 10x. So after you've done x1 plus 2x, the value of 10x will be 10 times x plus 1. So we've got speculative computations, and the fourth syntax we use is run S. S is a program. E is an expression that leaves a value on the stack. And if it's an integer value, it would terminate with int. And that calculates the value of running of the integer expression E after you've run S. Then it doesn't leave any traces because it reverses and just leaves the answer. So any side effects are undone by a reverse computation. My interest in reverse computation started at EuroForth, the 21st anniversary meeting, which was also our last. We talked half the night about reversible forth, which forth is so wonderfully simple, you can just completely change it. We decided in that meeting that what you needed to do was have another stack called a history stack, and as you run forward, you leave enough information on the history stack to be able to run backwards to where you came from. And that's what I implemented in this reversible forth, or we implemented, because a lot of people have contributed. So it says that any side effects produced by computing S and D are undone by their reverse computation. Computing an expression doesn't generate side effects in a normal sense, but it may produce garbage, but this also is computed by reverse execution. So you don't need to worry about garbage, and that gives you a very different way of being able to do things. So we represent a lot of values as parameter stack items. So I just take floating point numbers here. So floating point numbers are usually on their own stack. Here we have a floating point stack, but the user doesn't see it. Instead, we can have this kind of interaction. 2.0, that's a floating point number. It goes on the floating point stack, but also a pointer goes on it to the ordinary stack, to the parameter stack. When you duplicate that, you've got two pointers pointing to the same item, which you might suspect could cause confusion. So it's handled in a way where there is no confusion. So you duplicate, you can just think of it as you've got 2.0 on the stack floating point number, you duplicate it, put 1.9, let me say this. You got 2.0 on the stack. You duplicate it, you put 1.0 on the stack. You add them together. You do an F plus and an F times and an F dot. So that's duplicated a reference, but it gets the right answer. So what's going on? So the things that you can use safely are immutable. So an idea of what is immutable, the number 2 is immutable, or pi is immutable, or the set containing 1, 2, and 3, or the string hello world. If you change one letter in the string, it's a different string. Just as if you add 1 to the number 2, it's a different number. Something that wouldn't be immutable would be an array, because if you change one element of array, you still think of it as the same array. It would still be at the same, it would still have the same reference. And those are dangerous to duplicate. This is a trace of what goes on. So, when the command is 2.0, the floating point stack holds the number 2.0, and the parameter stack holds a pointer to the first entry on the floating point stack. So when you duplicate that, it just duplicates the reference on the parameter stack. Then you add 1.0, the floating point stack has now 2.0 and 1.0 on it, and you've got an extra reference to the second position on the floating point stack held on the parameter stack. So when you do an F+, it adds together the top two numbers, it adds together the two numbers pointed to by the top two entries on the parameter stack. But it doesn't do any management, getting rid of numbers because they're not needed anymore. All the numbers still there on the floating point stack. So again, when you do an F times, what it's taking is it takes the reference to the first entry on the floating point stack, reference to the third entry on the floating point stack, and you get the multiplication of those two items on the floating point stack. And then when you print that, the parameter stack is empty, but the floating point stack has got these numbers left there as garbage, because once a number goes on the floating point stack, it stays there until you reverse, but they're collected when you reverse your computation. So in that case, it was convenient to show it as the floating point stack, but if you have things of variable length like strings or sets, you would use a heap. But it's the same principle. You have pointers, but as long as the items you're pointing to don't change, you can be perfectly happy using references to items instead of the items themselves. One of the curses of reversible computing is that it undoes every computation as you run backwards. And you have to be very careful because it will undo your answer. So what you have to do is, after you've run a program and computed the value of an expression, if it's, you have to clone that so that, and that clone is not reversible, that is actually preserved. So that when you run backwards, you at least keep the answer that you got. Everything else is set back to its previous state. If you've got an array, you can, if you want to treat it like an immutable reference, we have an implementation of a immutable reference. The penalty is that if you change one element of your array, you get a completely new array. So then it's immutable because you generate a new copy of it whenever you change it. But it's more efficient for an array not to be immutable. And we can't use this technique without policing any duplication of references. So we might distinguish between values, and a lot of things can be values, but some things can't. And the things that can't, let's call them data structures. Data structures contain values, or they might contain data structures that contain values, etc. God knows why this has come out wrong. We use To reference an array, if we have a named array like array 1, val I of array 1 will get you the ith value of array 1. So that they're referenced by name. And I'm sorry for the whatever has gone wrong here. This laptop is usually connected to a big screen and separate keyboard and things. I just unplugged it, and there's obviously some difference in the configuration that this doesn't just display things. But to pass mutable references as stack arguments, we use call by name. So the meaning of so if you've got a subroutine which refers to some generic array, like my array, and you pass it array 1, you just have to replace every occurrence of my array with array 1 to find the meaning. That doesn't happen in execution, but to find what it means, you substitute the name of the thing you're passing to the generic name that's being used in the routine. So in our usage, call by name is a way of giving meaning to a program text that receives arguments passed by reference to named variables by substituting the names of those variables for the names of the corresponding parameters in the operation that's called. When we pass an argument by reference, array argument by reference, as long as we're passing a named array, the meaning of the resulting code can be described using call by name. This requires the use of named local variables that represent the array within the invoked operation. Call by name means more than one thing. This is a very, very simple kind of call by name. We just substitute the name of the, it just depends on substituting a name. So in the following definition, A is declared as a local variable which will reference an array whose address is passed as an argument when op is invoked. The phrase e to f of A assigns the value of expression e to the position f in the array. When we invoke op, passing actual array B as the argument corresponding to parameter A, we obtain the meaning of S for the purposes of semantic analysis by replacing each occurrence of the name A in S by the name B, where B is assumed to be a named array in the state space of the application rather than a reference. I've used local variables for a very long time with this kind of philosophy that local variables have types and there are different types of local variable depending on what they represent. So this is from an example from a paper I published in JFAR in 1985. It's matrix multiplication with local variables representing matrices created with the defining word mat. So here we've got mat M1, mat M2, mat M3, and you go into internal mat M4 and some indexes, and you are just doing a matrix multiplication in a loop. And I just thought I'd show that out of nostalgia. I was a robotics consultant in those days. So we keep our stack-based semantics as simple as possible to avoid modeling memory. So this is a very unambitious attempt at modeling Forth. Forth is an absolutely incredible language full of subtleties that I'm completely unable to conceptualize formally. Things like create, does, and but this I've been able to do. So wherever possible, we adapt to semantics of values. We regard references being values as long as the reference items are immutable. This technique generates garbage, but in a reversible language, this is automatically collected during reverse execution. Managing mutable references is really an open problem, but when passing a reference to a name mutable object, we can use call by name semantics. So in this work, it's the responsibility of operations like F+ to understand how to deal with the references they take off the stack. And Jonas Powell, if you remember, has a very nice type checking algebra that seems ideal for this, but I haven't applied it to it yet. There we are. Thank you very much.
Questions?
Thank you, Bill. Can you tell us how your paper was received yet? Have you had the presentation at the conference, or how did it work out?
No, this was a journal paper.
And have you had any write-ins or something like this, or when will the journal be released?
It was published in August.
Mm-hmm.
So
it was rather close.
It hasn't. I think we can safely say it hasn't set the world alight. The guy who first had the idea is called Rick Hayner, and he was a very leading computer scientist in the 1980s. When Tony Hoare, for instance, was 60, they commissioned a book of articles called A Classical Mind. And Rick Hayner was invited to write a paper. He wrote a 2-page proof of Gödel's incompleteness theorem. He's a very creative computer scientist. And he had, the way he explained his ideas was, when you have a set, you're doing two things at once. You're making a collection and you're putting it in a box. So we could usefully just make the collection and not put it in a box. And we might have a collection with nothing in. Now, an empty set is a bit like an empty box, but the contents of an empty box is a very, very intriguing concept because it represents nothing.
Mm-hmm.
If you ask ChatGPT, has mathematics represented nothing, you come up with absolute garbage. Lots and lots of suggestions that are all wrong. So as far as I know, Rick Hayner is the first person who's captured the idea of nothing. But he has his own mathematical system, his own logic. What we did was we took the classical way of making a mathematical theory, was you start with a logical basis, a formal logic, predicate logic, and then you put axioms on top, say, for example, for set theories and numbers, and then you have the structure of a mathematics. And if you go through that carefully, you realize that the logic has to change. And so we have a different logic which can argue about nothing. In classical logic, you can prove there exists x equal to 1 over 0. You can't prove anything about it, and it's considered harmless because it doesn't matter, because you don't know what it is, you can't prove anything about it. For us, it's absolutely inadmissible that there exists a number equal to 1 over 0, because if we divide 1 over 0, we get nothing. Because it doesn't correspond to anything, it actually represents nothing in our theory. So there isn't any. So that's why the logic has to change. Mm-hmm. So this has been years and years in the making, and it's been great fun. But when I retired, I thought, these marvelous theories of Rick Hayner, who's using them? There was one guy in Ireland using them. And I think, there was some guy on the continent wrote a book about parsing. I knew of 2 or 3 other people in the world that were using these, what I thought were marvelous theories. So he didn't set the world on fire. And I've got no chance, I'm just a nobody from Teesside.
Well, you will just keep the ball rolling, and
we keep the ball
sometimes
rolling,
maybe it will be set on fire. Who knows?
Let's know. Let's see.
Well, thanks for your effort, Bill.
Thank you very much.
So, maybe there's some other questions. So,
that was one.
Are you still dependent on a particular version of GCC?
No, we wrote, our forth is written, there's a meta compiler that generates 8086 assembler, AT&T assembler, it's a GNU style assembler. And that, along with sections of the code that are written in C makes our fourth nucleus. So it's an original thing. It doesn't base itself on any fourth. Although I suppose I'd written several fourths before, for instance, when I was a robotics consultant, and I was a consultant for the BBC Automated TV Studio. So I had a lot of culture of fourth systems ready to kind of be modified and used for this purpose.
Further questions? So I have a question. So do you have some example programs for your system?
Yes, we have. We don't have as many example programs as we should because we spent an awful lot of time on the mathematical theory. But one nice example program is the Knight's Tour in chess. So your problem is you start anywhere and you have to find a way to visit every square and come back to where you started. And the trick for making it easy is use up squares that have got few exits because they risk turning into dead ends. So when you're looking which square to go to, you choose something that's got a minimum number of exits. And that uses this idea of speculative computation. You know, you say, suppose I move there, how many exits would I have? And then arrange those in a table and choose one of the constrained squares. So that's if you like, the example program.
Oh, thank you. Further questions? All right, let's thank the speaker again.